I've picked a homework problem out of the textbook from chapter 4 and would like to show you how to work it out from start to finish. Because in chapter 4, you're transitioning from mostly working on closed systems into working on a category of real world problems that are open systems. So let's get started so I can illustrate how you would solve a very representative open systems thermo problem. This is going to be problem 422 in your textbook. And it has to do with analyzing the flow through a nozzle. And here's a picture of a real world nozzle. This is a Sidewinder missile rocket nozzle. And here's the problem. It says air with a mass flow rate of 2.3 kilograms per second enters a horizontal nozzle operating at steady state. That's a key, steady state at 450K, 350 kPa. So that's the inlet pressure and temperature, and a velocity of 3 meters per second. At the exit, the temperature is 300 degrees K. Okay, let's see, it's getting cooler. The velocity is 460 meters per second. Flow is getting much faster. Using the ideal gas model for air with constant specific heat, Cp equals 1.011 kilojoules per kilogram degree K, determine two things: the area of the inlet of the nozzle, and B, the heat transfer between the nozzle and its surroundings in kilowatts, and specify whether the heat transfer is into or out of the air. Well, okay, well, let's get started without disclosing whether it's going to be easy or hard. Let's get started. Okay, and so anyway, here's a little bit of a photographic sketch. Here's the inlet of our nozzle. Here's the outlet. Okay, so for example, here's a cutaway view of a Hellfire missile nozzle. Here is the inlet, larger diameter. Here's the outlet, smaller diameter. Okay, and so I hope you see that these are classic pieces of equipment to increase the velocity of the gas flow. Okay, first thing let's do is let's reread the problem and look for key words and clues to solving the problem numerically. Okay, air, that's going to be an ideal gas. Okay, let's jump down here where we saw constant specific heat, constant CP. So that's going to be a simplification for modeling our air as an ideal gas. Okay. Also, keyword nozzle. Nozzle, that's a special type of equipment. And so now I hope that you're seeing with your eyes what a nozzle looks like. You're going to be able to tell some simplifications of modeling that nozzle. Let's see. You're also given velocity at the inlet and the exit. That is a clue. When you're given velocities in a problem, that is a clue that you're going to need to include changes in kinetic energy. That's an immediate clue to you. All right, so let's see what bullet items of what we've got. We've got an open system, steady state, steady flow. So that says the mass flow rate going in exactly matches the mass flow rate going out. In other words, this nozzle is not getting fatter or skinnier as time goes by. Things within the nozzle are not changing in time. Okay, steady state, steady flow. Substance, air, it's an ideal gas, and we're directed to use constant specific heat. Now, that means we may not use table A22. Table A22 is for air, but modeling it as with a variable specific heat. So it would be technically incorrect to get property data from table A22 for this problem. We must use constant specific heat. Type of nozzle. It's a nozzle, type of system. Now, can you visualize here? Do you see a rotating shaft coming out of this open system? No. Is this open system lifting a weight as part of its process? No, it's not. So that tells you, your common sense then tells you when you have a nozzle, there's not going to be any power or work associated with the process. That's going to be key for you. Velocities are given, kinetic energy changes are going to come into play. The other thing, part B, it says determine the heat transfer. Now, that's a code. So far in this class, the only tool you have in your toolbox to solve for the heat transfer is the first law of thermodynamics. And so when you start seeing determine the heat transfer in your mind, you immediately think, I'm going to need to write some form of the first law of thermodynamics to solve for the heat transfer rate. Heat transfer rate. Now, here it just says heat transfer, but look, we've got to read between the lines, recognizing we've got a flowing system. And so really what you're looking for is the rate of heat transfer, Q dot, not Q, Q dot. If you're interested in learning more about nozzles and diffusers, I'd like to chase you to my Jay's Toolbox YouTube channel and see if you can find the video Nozzles and Diffusers and browse that to see if that can help you. Well, now we're ready to start solving the problem. Let's start with a sketch and plan our work. Here's our sketch. Pretty simple, okay? A nozzle, so you're going to show it sort of as a trapezoid with the diameter decreasing, area decreasing. Here's our given information that was given in the problem statement. And I'm going to add to the screenshot of the textbook sketch, Q dot N. That's what we're solving for. Q dot N. Is it going to be positive or negative? We'll discover that when we get the numbers out. But we always show Q dot in. We don't show Q dot out. Similarly, W dot out, I hope I've convinced you. So I've shown an arrow, W dot out, and I'm clearly showing that E equals 0. The output power of this nozzle is 0. That's going to be important for us. Okay, let's plan our work. Part A, we're asked to find the area, okay? And I see that I've moved my text box and I've obliterated what it says here, so I'm going to have to remember it. It says, recall, m dot equals rho times A, area, times velocity. And remember, m dot is rho AV. Another thing that you remember, hopefully, is that m dot also equals area times velocity divided by specific volume. And that's what I've obliterated with my text box. M dot, the mass flow rate, equals AV, that's the volumetric flow rate, divided by the specific volume V. And so my claim here, we've written, do you see that, wow, you've got plenty of information here for an ideal gas, pressure and temperature at state 1 to determine the specific volume of V. And remember, rho, density, is the reciprocal of specific volume. So we're going to be in good shape on finding the area. Okay. All right. So now the heat transfer, we're going to use the first law for an open system, steady state, steady flow with one inlet and one outlet. I am hoping that you can get that statement of the first law into your head without going to a formula sheet. That is my hope, because you're going to be using this approach over and over and over again throughout the rest of this class. Ideal gas questions. Were you a little confused when I said we're going to model this air as an ideal gas with constant specific heat? I need some refresher on that. What's the difference between constant specific heat and variable specific heat? I'd like to chase you to my YouTube channel and look for Ideal Gas 03. I've got a video that lasts about 50 minutes that really in detail talks about modeling ideal gases. Well, let's write down some fundamentals about ideal gases in general. R, the gas constant R. Well, what was that? That's R bar over the molecular weight. That's true for all ideal gases. And do we, hopefully in our head, we remember that R bar is 8.314 kilojoules per kilomole degree K. I have missed kilojoule per kilomole degree K. I didn't type that out, a typo. And the molecular weight of air, 28.97 kilograms per kilomole. That's for air. We should have that in our heads because we engineers deal with air so much. Molecular weight of air, basically it's a mixture of oxygen and nitrogen. Molecular weight, 28.97 kilograms per kilomole. All right, another thing we remember about an ideal gas equation of state, P times little v equals RT. So we can solve for little v. V is RT over P, and rho, density, is P over RT. Those things you have in your head, I hope. Another important thing, relationship for any ideal gas is C sub P, that's specific heat, minus C sub V, specific heat, equals R. Cp minus Cv equals R. I hope that you've got is, how would you calculate the change in enthalpy, H? For any ideal gas, the change in enthalpy of H is the integral of Cp dt. And the change in little internal energy, little u, is the integral of Cv dt. Now, back to our specific problem. It says, use ideal gas model with constant specific heat. So do you see with your eyes, well, if Cp is a constant, 1.011, you simply pull it out of the integral, do the integral, and you come up with the very nice, handy result for ideal gases with constant specific heat. Delta H is Cp times delta T, and delta, little u, is Cv, constant number, times delta T. And gosh, looking ahead towards other problems, or a quiz, what if you're given Cp in a problem, told to hold it constant, but you found that you had to use, you're looking for delta little u. Gosh, think that instructor's playing a trick on me. No, you need Cv, so you remember in your head that Cp minus Cv equals R for all ideal gases. So if you're given Cp and you need to find Cv, you will not, for this problem, Cp minus Cv is equal to R. Okay, we're still planning ahead. We haven't put pencil to paper yet with numbers. How do we get to one equation and one unknown for Q dot? Q dot N, that's what we're looking for. How do we get to one equation, one unknown? We write the first law of thermodynamics, and hopefully in our heads, we can reduce the general statement of the first law into a simplified statement of the first law for steady state, steady flow, one inlet, one outlet. So it is my hope that you can plop down this in your homework solution. Now, not without simply copying this down blindly. This is not a formula. It's something you can get from the general statement of the first law. Q dot in minus W dot out, for our problem, that's going to be 0. It's a nozzle, equals M dot. There's only one M dot, one inlet, one outlet. It's steady state. There's M dot times bracket, change in enthalpy, H2 minus H1, H out minus H in, plus 1/2 V2 squared minus V1 squared. That's the change in kinetic energy of the flowing fluid. And let's check off what we know. M dot given, V2 and V1 given, H2 minus H1. We need that. Well, how will we get that? Oh, we've already planned this out. H2 minus H1 is integral Cp dt. For constant specific heat, we simplify Cp times T2 minus T1. Cp is a known number. Let's see, T2 and T1 are given in this problem. It kind of becomes child's play, doesn't it? Oh, but one, not exactly child's play, because we've got to keep our units consistent throughout the right-hand side of the equation. So look ahead. What's delta H going to be in? It's going to be in kilojoules per kilogram, isn't it? What's V2 squared minus V1 squared divided by 2 going to be? Meters squared per second squared. So we cannot blindly just plug numbers in and get a numerical result. We got to keep our units straight. I'm going to review with you how to do that. Okay, units. If you want a refresher class in units, please go to my video and check out Working with Units Part 2. This is where I address kinetic energy units. If you're having trouble with kinetic energy units, please go and look at this video. Okay, we're planning ahead, and we've got this. We already know that we're going to have a delta H term and a delta kinetic energy term, and we're going to have to get our units straight. And so this is simply a screenshot of something I did in 2022 to derive what's the relationship between kilojoules per kilogram and kinetic energy change in meters squared per second squared. And so I'm not going to drag you. This is any engineer should be able to do this derivation. That means you, okay? We go through and we discern what's a joule? Well, it's a Newton meter. What's a Newton? Well, it's a kilogram meter per second squared. Now I'm down to basic units, and I can see that 1 kilojoule per kilogram equals 1 kilo, that's 1,000 meters squared per second squared. And so here is our conversion factor. So you can derive this. So here's your jackpot conversion. And I'm not even sure it's in the book in your book on conversion factors, because the book figures you can derive this on your own. 1 unity equals 1 kilojoule per kilogram divided by 1,000 meters squared per second squared. And we will use this in this problem and other problems that involve kinetic energy. This first law, you say, oh, I don't understand where he was talking about this first law. What's this first law stuff? I've gotten a little behind in class. Let me suggest that you look for my first law crash course on video. So I try my best to quickly, in 42 minutes, go through from general statements of the first law to specialized statements of the first law. And I try to give you some tips on how to get all of those into your head without relying on a formula sheet. You will discover that formula sheets slow you down in the long run when you're taking a quiz and test. All right, so now we're going to solve the numerics of this problem. Okay, we're going to write down part A. What is the inlet area? What's the inlet area? M dot equals rho AV. So we're going to write M dot given, velocity given, T1 and P1 given, and T1 given in degrees K. That's good. Absolute temperature. We're going to write down our bar. We know that in our heads. Molecular weight. We know that in our heads. So R for air, if you don't know it, if you haven't committed it to memory, R for air is 0.287 kilojoules per kilogram degree K. And look here, I correctly stated the units of R bar compared to what I did earlier in a slide where I made a mistake. Okay, so let's see, V1, ideal gas equation of state. It's going to be V, specific volume, is V1 is RT1 over P1. Got that in our heads. Don't need a formula sheet. 0.369 cubic meters per kilogram. Okay. So now we can flat out solve for the area. M dot equals rho AV, or M dot equals AV divided by V. And so A1 is 0.2829 square meters. Not so bad. Okay. The next thing, now we're looking ahead, we're going to apply the first law of thermodynamics to solve for the heat transfer rate. So look, instead of going right to that, why don't we calculate the changes in enthalpy and the change in kinetic energy, so we'll have numerical results for that before we go to the first law. Okay, so let's see. The change in enthalpy, Cp times delta T. Okay, so we'll write down what's given. Okay, write down Cp, given. So the change in enthalpy, H2 minus H1, outlet minus inlet, is negative 151.65 kilojoules per kilogram. Easy. Okay, a little tougher. Velocity given 460 meters per second, leaving V1, 3 meters per second going in. Okay, change in kinetic energy, V2 squared minus V1 squared over 2. Turn the crank on your calculator, you get a huge number, 105,795.5 meters squared per second squared. Wow, numerically, whoo, look at the difference numerically between these two changes. Something can't be right. That's your clue to say, I've got to get, my units are not consistent with each other. A kilojoule per kilogram, meter squared per second squared, not correct, not uniform. So I've got to remember my conversion. 1 kilojoule per kilogram is 1,000 meters squared per second squared. So I'm going to apply that. So I simply move my decimal place 3 places to get the change in kinetic energy in kilojoules per kilogram is 105.8. V2 squared minus V1 squared, all divided by 2. 105.8 kilojoules per kilogram. Okay, so now we're back to applying the first law to solve flat out for the heat transfer rate. Q dot N equals minus W dot out, 0. M dot, we've got it. H2 minus H1, we've got it. 1/2 V2 squared minus V1 squared, we've got it, and in the correct units. So here we go, just plopping that down. And so Q dot N is negative 105.5 kilowatts. That's kilojoules per second. M dot, kilograms per second times kilojoules per kilogram. That's going to be kilojoules per second or kilowatts. And in the problem, it said, say whether the heat transfer is into or out of the nozzle surface. Well, the answer would be the heat transfer is out of the nozzle surface into the surroundings. And so it would be a nice gesture to write that out in a sentence, since that was asked in the problem. Not so bad. Okay, so let's recap what we did. Always start with a sketch. Do you see that how much we referred back to the sketch throughout the problem? We planned our work before we started scratching down numbers. We started with thermodynamic fundamentals. We didn't go to a formula sheet. We didn't start paging through the book to look for formulas that might help us. That's a loser, because you're not preparing yourself to do well on a quiz or a test if you are using a formula sheet or paging through the textbook for looking for formulas that might work. We checked our units as we went along. So this was a classic problem where units were not consistent if you just crank through the numbers. You've got to be checking your units as you go along, not just on the bottom line. Okay. Express results, including units, which I always do in my solutions. So that's it. How would you classify that problem? Very difficult, very easy? Probably somewhere in between. You'll classify it as very easy once you've done a couple of these. I hope that has helped. So I hope giving you a solution to a fully worked out open system, steady state, steady flow problem in chapter 4 sort of helps you see, maybe get you started if you're having trouble getting started solving these problems. The more homework problems you solve, the better and better you're going to get at performing on quizzes and tests. Hope that helps, and I hope to see you again soon.